Yeah, I think we can start, right? So then again, hello everyone. My name is David Scheer. I'm a PhD student in the group of Fabian. And today I'm going to present my work on a paper or on the superconducting clock circuit, which is a device that we wrote a paper about, which is able to improve the coherence of Josephson radiation beyond the thermodynamic uncertainty relation, which some of these words might seem a bit new, but I think I will explain the stuff during the talk. So maybe let's start a bit with our background, why we are interested in such a topic. We in the last years we have worked on high impedance electronics, which are circuits with a characteristic impedance that is above the quantum resistance, so above this 6.5 kilo ohm in a superconducting setting. Also, the circuits themselves are superconducting, but the devices have a high characteristic impedance. And those have various applications, for example, in quantum metrology, where they can be used to create dual Shapiro steps, which are at the moment on the frontier of trying to create a metrological standard for current. So closing this quantum metrology triangle that defines electrical units, or that allows for a self-consistent definition. But also these circuits have applications in quantum information, where they can be used to design different superconducting qubits like the fluxonium or a 0-pi qubit. And these circuits are for these circuits, it's very interesting to think about the concept of on-chip driving, namely because supplying AC signals is experimentally very challenging if you have a high impedance environment. So first of all, I mean, there's all this trouble of heating your device in a fridge and stuff like that. If you have transmission lines you want to put in there and further on. But also, if you have a high impedance device, you have an impedance mismatch between the transmission lines, which are usually 50 ohm, and the high impedance device. And furthermore, what might be even worse in some contexts, you can have parasitic capacitances, which may shunt your high impedance environment and destroy it altogether. So the idea is that you don't need to input AC radiation from an external device, but rather try to generate it on chip using the AC Josephson effect, which can be very useful for also miniaturization and scalability in quantum information processing devices. So what is the AC Josephson effect? Maybe just a brief reminder. Let's say we have such a Josephson junction right here, which has a current to phase relation with a superconducting phase of just the current is given by the critical current times the sign of the superconducting phase. Then if we apply an ideal voltage bias, we know that the superconducting phase just grows linearly in the applied voltage. So therefore, we get oscillations of the current with a frequency given by the voltage, which might be interesting in of its own. And for example, one can use this to drive such a device with the so-called phase slip junction, which is of interest for the quantum metrology and the dual Shapiro steps, which we proposed in a paper of ours from last year. And now, of course, there's also various very sophisticated on-chip sources already that are based on the Josephson effect. And they have a huge range. For example, there are single photon sources, which are bright and can be used to reliably create anti-bunched photons. There's a Josephson laser where basically a cavity is pumped by a Josephson junction, as far as I understood it, because we have an expert here in the audience. So yeah, but exactly, we have this cavity that is pumped by a Josephson junction, and there's also various devices that are based on self-locked Josephson oscillations. So the oscillations created by a Josephson junction are fed into a resonator, and they somehow couple to each other and lock the phase of the oscillations to a certain value, which in recent years has also become even more sophisticated, where they are able to create even frequency combs using this and not only monochromatic continuous wave radiation. And now maybe the question I showed you before, this simple picture of a voltage bias in the Josephson junction, which portrayed perfectly sinusoidal oscillations. So now maybe why are these devices so much more sophisticated than just a junction with a bias? And it turns out, of course, in an actual experiment, you don't get ideal voltage sources, right? You get this real voltage source, which might be a current next to a large conductance, and then you can get an effective voltage bias. However, this changes the dynamics of the Josephson junction and of the phase, because now you don't get these completely sinusoidal oscillations anymore. And instead, for example, what you can look at is a DC voltage, that corresponds now to a frequency of the oscillations across the Josephson junctions. Here you can see an IV curve. So now this critical current also makes sense because below the critical current, there are no oscillations and no voltage. And afterwards, we get this square root-like behavior here. And this voltage directly corresponds to a frequency of the oscillation. However, now, since this real voltage source also has a dissipative element, we get thermal fluctuations from Johnson-Nyquist noise. And it has been known for a long time that these drastically reduce the coherence of the resulting Josephson oscillations. Namely, this dephasing rate here is given by some prefactors with 2 times Boltzmann's constant times temperature. And then the important part here, it's proportional to the differential resistance squared across this curve. And you see already that this is the differential resistance here above the critical current, where you actually can see oscillations, is a lot higher than just for this ohmic dissipative element. Namely, we get a bound on the so-called uncertainty product, which sort of quantifies the entropic cost you need to maintain the steady state of an oscillation. So here we have the variance of the superconducting phase over the expectation value squared times the entropy production rate, which is basically just the energy dissipated across the resistive element for a certain current bias. And this is given by 2 times the Boltzmann's constant times the differential resistance as well as this biasing conductance here. And as it turns out, this biasing conductance actually presents a lower bound for this differential resistance. So therefore, this uncertainty product here is bounded by 2 times the Boltzmann's constant, which also directly impacts the quality factor of this whole resonator, of the oscillations. Because this quality factor, I don't know how familiar you are, states basically how many oscillations can I do before I lose the phase coherence, which is of course very important for if you want a steady on-chip radiation source. And it turns out you can't really exceed this value, and basically the only parameter you get to tune the frequency, because the frequency can vary along this curve. So the only parameter you get to you obtain to tune sort of the coherence properties is this biasing conductance here, which if you can make it arbitrarily large, of course you can also get this quality factor arbitrarily large. However, the larger you make this conductance here, the more heat you dissipate into your system. So the more you heat up your device, which is maybe also not what you want really. And now this uncertainty product has actually been extensively studied in the field of stochastic thermodynamics, where it is known under, or this limitation is known under a different name, namely the thermodynamic uncertainty relation, which is defined for just Markovian systems in a non-equilibrium steady state. And again, it basically presents a trade-off between the precision of a general integrated current and the entropic cost that is required to maintain this non-equilibrium steady state, right? You're out of equilibrium, so in your steady state, you constantly produce some entropy. And this uncertainty product is again bounded from below by 2 times Boltzmann's constant, which can be seen sort of as a refinement of the second law of thermodynamics, which you can understand here in the right figure. So here, this gray bound here is just the second law. So if we have a system and a medium, the overall entropy production has to be positive. But now there's even further restraints on that, which can be understood in the sense of this thermodynamic uncertainty relation. And what is important, which has also been shown by Deschamps and Zaza, is that this uncertainty relation also holds in the setting of overdamped Langevin dynamics. Meaning if we have here now a first order differential equation, right, with this integrated current variable y, for example, and then some dependence here, which is basically the current to phase relation of the Josephson junction and the bias current, plus some independent Gaussian white noises, so just the thermal fluctuations from the Johnson-Nyquist noise. Also, this thermodynamic uncertainty relation holds. So sort of now we wanted to try to understand how can we achieve precision beyond the thermodynamic uncertainty relation. And also people in the field of stochastic thermodynamics had a lot of ideas how this might be even universally applicable. But and sort of now what sparked also our development of the circuit that we did is this talk here by Pizonka about the thermodynamics of clocks, where he basically showed that this precision of the uncertainty that is sort of bounded from below by this uncertainty relation can be drastically improved when you couple to underdamped systems, which is, for example, exactly what a pendulum clock does. So if you just want now to measure the passing of time, right, one primitive idea might be just to have a weight and have it go down with a friction where you have this wheel here, right? But there you get fluctuations which give this bound by the uncertainty relation. So just the movement here of this weight, like in a grandfather clock, might be not enough to really get a precise timekeeping device. Of course, you also have an energy supply, which is basically just the pull of gravity in a standard pendulum clock setting, but of course can be something else. And the idea is now you need to regulate the velocity of this counter somehow. And this you do via this oscillation. So of course you need something periodic, right, in order to really keep track of time and to count somehow the oscillations of this pendulum. But the pendulum, of course, also loses energy because you have friction and stuff like that. And this is where the escapement coupling comes in. Because an escapement has basically two roles. First of all, it regulates the motion of the counter. So therefore, the velocity with which this weight moves down is governed by the frequency of the oscillator. And second, it has to be designed in such a way that the energy that is supplied to the counter basically arrives at the oscillator in order to maintain a steady oscillation with a certain frequency. And now let's consider maybe a minimal model. So we have this overdamped counting degree of freedom here with a damping rate gamma. We have the external force F, which basically corresponds to a current. And we have also a harmonic oscillator. Here is the important part. Since this harmonic oscillator is an underdamped system, we get this inertia term for small damping rates, which allows us to go beyond this thermodynamic uncertainty relation. So this is exactly the ingredient which we need, which also maybe explains again why all the devices for Josephson radiation I showed you before are couple a junction to a cavity, because there you get this underdampedness in, which allows you to achieve higher precisions. In addition to that, now the centerpiece of this clock is the escapement potential here, which can be simply realized by this nonlinear coupling between the position of the pendulum and the position of the counter, where the position of the counter, of course, is periodic in the sense, yeah, this wheel spins, so at some point you arrive back at the start with a coupling strength couple. And then for this, you can generate a coupling between the two. And now if we want to implement this in a more, let's say, practical setting for superconducting circuits, we can construct a circuit basically out of analogy with this pendulum clock, where the counting degree of freedom is just the superconducting phase here across the biasing conductance, with an energy supply, of course, given by the external current. And the oscillator is just a standard RLC oscillator. So here we have a resistive element, which can basically also just be understood as energy losses to either environment or, of course, also as a load impedance. So here you could put the device you want to drive, for example. And furthermore, we get this escapement coupling here, which we can realize by two Josephson junctions. So we are sort of close to a squid loop. And we also have to be at maximum frustration. So we really have to put this external magnetic flux here to half a flux quantum. And with this, we, like in a frustrated squid, we suppress this lowest order coupling here to arrive basically exactly at this first order x times psi and y potential. And so now these are the basic building blocks. And now maybe let's get a bit more into the details of how we can actually describe such a circuit or what is an appropriate model for this. So the framework that we chose is we did a hybrid description. So we started with the counter, which has an overdamped motion. So the biasing conductance here is much larger than the quantum conductance. And with this, also inspired from our knowledge that we basically have this linear velocity, which we regulate by the frequency of the counter, we started with the linear growth that is given sort of by the frequency of that is given by the frequency of the oscillator, plus a phase modification, which might be slow. And overall, with this, we arrive at a Langevin description of this effective degree of freedom here, which is the phase of the growth. And with this, we sort of get an equation with the damping rate, right? We get this external energy supply, which is basically given by the frequency mismatch. So this current over the decay rate sort of defines a frequency.
And we can compare this to the frequency of the oscillator. We get some nonlinear force that is based on this phase variable theta here, as well as a stochastic force, which is again just Johnson-Nyquist noise. For the oscillator, we are interested in an underdamped description. So we want the damping rate here given by this conductance to be a lot smaller than the natural frequency of the oscillator, where the impedance here is just calculated for a lumped element oscillator. And with this, we are able to make a rotating wave ansatz for the superconducting phase here of the oscillator, where we can relate the cavity operators A and A dagger to the superconducting phase via this light metal coupling constant here, which again compares the impedance of the resonator with the quantum resistance. And with this in the rotating frame, we can arrive at a Lindblad description, where we get a coherent evolution according to some rotating wave Hamiltonian, as well as these jump operators that enforce a thermal photon distribution in the cavity. And now the escapement coupling here, we also do it for a more general, in a more general setting, but the interesting regime for us is, where we can also do analytics, is the regime of weak light metal coupling. So the light metal coupling constant times the expected photon number should be small in a sense. And with this, we get an effective rotating wave Hamiltonian here with the coupling strength proportional to the critical current, which is very close to this escapement coupling here by Pizonka. And now let's come back. So what couples the two systems is the fact that this Hamiltonian depends now on the phase theta of the counter. So now we get here basically a driving term in the oscillator, as well as here now we can explicitly calculate the force, which is just the derivative of the energy or of the expectation value along just the oscillator. So calculated with respect to the density matrix of the oscillator of the derivative of the Hamiltonian function. So pretty much just again a force. And now with this, we care not only about the regime of the small light metal coupling, so sort of a controlled photon number, but also in a sense about large photon numbers, since we want really the dominant effect in the state of the oscillator to be a coherent state with a coherent photon number that is much larger than 1. And this allows us to make again this rotating wave ansatz here for the phase of the oscillator, where it's just the real part of some amplitude times some oscillating term. And with this, we get actually some Adler type equations for the behavior of the phase of the counter as well as the oscillator. Where you can see here, we have again first order differential equation. And if you don't know Adler equations, the sort of typical thing for these is this nonlinear cosine or sine coupling between the phases. And this is a hallmark feature of synchronization. So we can actually solve this equation by making an ansatz where we say that the phases of the oscillator and the counter sort of evolve at the same velocity, so that their difference remains constant over time, which allows us to make an ansatz with a steady state amplitude, which we can now calculate explicitly if we solve this cubic equation here for the tangents of the steady state phase difference, where the synchronization strength beta determines not only sort of how well the systems can synchronize, but also gives us hysteretic behavior if it's above a certain value, which is very similar to the dynamics of a Duffing oscillator. And the point here is that we have basically, so now if we look to the right at this IV curve, so let's remind ourselves again, the voltage of the counter, which we plot here, is basically also the velocity with which the weight moves down for the pendulum clock. So of course, if there's no external force, we don't really get a movement. And then we get this linear growth here in the beginning. So this is just the normal ohmic behavior, basically, until we run into this resonance here with the oscillator. And there we can really see that the counting velocity saturates into a plateau that is determined by the frequency of the oscillator. And if the synchronization strength is large enough, we also get this hysteretic behavior here
where we have a competition between the regime where between the state where the oscillator enforces its frequency on the counter and where the counter off-resonantly drives the oscillator. So therefore, of course, here we don't get really an influence of the oscillator because it's driven off-resonantly and therefore has a small amplitude. And the point is, with this solution from our classical synchronization, we can obtain analytical results that fit to the simulation of the full hybrid quantum system, so with a Lindblad equation and a Langevin equation for small light values of the light matter coupling. You can see here that this blue curve matches the analytical description quite well. And now with this, we can furthermore consider the stability of the actual radiation, which we can improve now beyond thermodynamic uncertainty relation. So now let us come back to this biasing conductance here and just consider how the phase variable evolves in time. And for this, we had the simple IV curve here, the orange dashed line, which is basically just the ohmic resistance. And you can see sort of that on this clock resonance, the circuit deviates from that. And in particular, here we can plot the uncertainty product. Remember again, this orange dashed line for the ohmic resistance is the minimal bound for the precision of the superconducting phase in an overdamped regime. So we can really now see here that we get a strong violation of the uncertainty relation of the thermodynamic uncertainty relation when we are on this resonance plateau. And this corresponds basically one-to-one with the differential resistance across this curve. So remember in the beginning, we argued that as long as the differential resistance can't be smaller than the biasing resistance, we are limited by the uncertainty relation. And once we drop below this, we can really also just see that the uncertainty relation is broken in the same way. So now instead of this old bound with just 2 times the Boltzmann's constant, we get a new uncertainty relation, which is basically limited from below by the quality factor of the resonator, as well as the synchronization strength beta. So basically, we might not even get a bound because we can, at least in theory, make this here arbitrarily small. And furthermore, we can look at the quality factor of the radiation emitted by the oscillator. And with this, we can see an improvement by a factor 1 plus beta squared. Again, beta is the synchronization strength here, where we can really see this Q0 is the maximally achievable quality factor for the given frequency if we have this Josephson, if we just have Josephson radiation. And now with this clock circuit, we can really see an improvement here by roughly 2 orders of magnitude. So this really improves the line width as well of the emitted radiation. So in a more experimental setting, we, of course, if one wanted to implement this, we really need to keep track of the approximations that we did. So we need that this biasing resistance here has to be a lot smaller than the quantum resistance. We want an underdamped oscillator. And what we need in order to control the nonlinearities in our system is a photon number that is with the light matter coupling in a sense a bit small. And this is given, this we can also express in the circuit quantities. We can also take a look at the dephasing rate, which corresponds to the line width, which is then scales 1 over coherent photon number squared. And we get a free parameter here, which is the impedance of the resonator. So if we make the impedance small, we can get a good a small dephasing rate, which corresponds to a good quality factor of the oscillations. Furthermore, we can also take a look at the output power, which scales with the critical current squared. So we know how to increase this, at least in principle. And now the problem, the bottleneck is sort of this impedance of the resonator, because this is hard to make small. So we talked to some experimentalists and they told us that 5 ohm might be a good value. So we sort of centered everything else around that. We also, because we saw before that we still get this plateau, which we think corresponds to a good quality factor of the radiation outside of the regime of controlled photon numbers. So where the light matter coupling is not small enough to get this smaller than 1.
So we sort of pushed these other formulas, which we can only obtain from the analytics for a controlled photon number, sort of to the limit where we think this approximation might still be valid. And there we get a line width at a frequency of 5 gigahertz. We get a line width of approximately 4 kilohertz and an output power of 1 picowatt. Again, the synchronization strength here now is roughly 93, which is a lot larger than in our previous simulation where we did like 5. And if we compare this to other state-of-the-art radiation sources, so if we operate as well as at a temperature here of 10 millikelvin, we can see that our line width is very comparable to also other devices where this 4 kilohertz here appears sort of as a rather good value. And our output power of 1 picowatt is also sort of on the higher end, but not as large as compared to this example. However, in this other device where they did the self-synchronization of Josephson oscillations as well, the critical current was at 10 microampere, so basically 2 orders of magnitude larger than the one that we used in order to stay true to all our approximations. However, we think that this can be pushed further with increasing the critical current, or at least we would expect that this would hold. And so now we learned some stuff of how we can create good radiation sources by using the thermodynamic uncertainty relations, really getting ideas from the field of statistical thermodynamics. So maybe in the other way around, what can we learn about the uncertainty relation maybe? So what we can learn is that apparently superconducting circuits, also the ones used for a longer time, can sort of very easily break this uncertainty relation. So they really provide a good test bed and considerations to think about these kinds of things. And what our work indicates, and what we also saw in other works, is that where it was not stated explicitly, is that a sub-ohmic differential resistance might be a hallmark feature of the violation of the thermodynamic uncertainty relation. Because in our IV curve, as soon as it gets flat, you can really see a nicely aligned violation of the uncertainty relation that corresponds to the differential resistance squared. Also, in other papers we saw, we again got this voltage plateau here for varying bias currents for these radiation sources, or for example, also in a device in a Josephson spectrometer that was rather similar to our device. There was as well this loop mode in a frustrated squid, which is a very well-known feature that it reduces the line width of the noise if you bias across this. So there we can really see that this might be worth investigating if one wants to understand the thermodynamic uncertainty relation more in the context of superconducting circuits. So yeah, overall, what did we do? So we noticed that the coherence of Josephson radiation is limited by the thermodynamic uncertainty relation in the context of overdamped Josephson junctions. And we visited a talk that showed us that this uncertainty relation can be broken by a classical pendulum clock, which inspired us to design our circuit in a way that it really reproduces such a minimal model of a clock, which first of all gives a stable source of DC voltage, which might be also interesting of sorts, which really shows that the uncertainty relation is broken and there might not even be a bound for this uncertainty product in the context of underdamped systems. And we managed to improve the coherence of the output radiation by a factor of the synchronization strength squared, which can cover several orders of magnitude. I think this was all for me. Thank you for your attention. And of course, if you have any questions, now would be a good time to ask.
Hey, David. I have a couple of questions. Thanks for the nice talk, by the way. Earlier, you have this uncertainty at the near the introduction. You have this uncertainty product with an omega over temperature factor.
After?
So not this one.
No. That was maybe it was an earlier. This one, yes. Very good.
Yes.
Now, is that assuming a particular regime or relationship between the temperature and the frequency, or is that generic, even for low temperature?
I think this should be generic. So I would assume, at least for these Josephson junctions, I haven't thought like explicitly about quantum noise,
Yeah.
but I would expect that basically, since we saturate into an effective temperature, right? I mean, that's sort of the effect of quantum noise in these simple settings, right? And then for the effective temperature, I would expect a similar relation, because we just can't go below a certain noise temperature, right?
Right. Right. That I guess it's interesting because at 10 millikelvin, we expect to be well below the frequency scale.
Yeah.
So I think in a lot of experiments, we would in fact expect to be in this quantum limit.
Yeah, that's true.
Hmm.
I think, yeah, for the uncertainty relation, this is not so pressing.
Right.
Because there we consider basically the zero frequency. So we consider the DC part, and of course there the frequency scale is then again not relevant for the temperature. So they were always in the classical regime. But yeah, of course you're right, for the oscillations, one might treat this a little bit more carefully.
Hmm. If there aren't other questions, I have one other one, which was whether, at some point you're taking some RWA approximations in the math, but I guess your simulations, do your simulations also take an RWA approximation, a rotating wave approximation, or no?
Yeah, they did as well. And the thing that justifies this, in a sense, is that so this is also in our paper, we checked that if we really realize this escapement coupling, we managed to suppress the fast rotating contributions that might have down conversion effects.
Okay.
So in a sense, this is, I
But
would
so,
say,
for
still
example, if the critical currents are not identical, then those terms may play a role.
yeah, then those terms might play a role.
Okay.
But yeah, in the simulations we discussed that was accounted for. That was not in the rotating frame.
Got it. Yeah. Okay. Thank you.
Welcome.
Are there any other questions from the audience? Okay.
Doesn't seem like it.
I guess so. So thanks again, David.
Oh, you're welcome. Thanks for the question. So yeah, I think then we're done here, right?
Bye. See you. Have a nice day.
Bye, you too.